Why can we be sure that there is life in space? The answer can be summarized in a few words: because the universe is practically infinite in size. According to current estimates, it contains about 2 trillion galaxies, each of which in turn consists of an average of 1 trillion stars. So in total there are roughly 1 quadrillion stars, and we are talking here only about the observable universe. Thus the part of the universe, from which so far the light of the stars reached up to us. How large the universe is beyond that, we do not know. Since stars are often orbited by several planets, there should be even more planets than stars in the universe, and thus the probability is high that among them there are also planets which resemble our Earth. Not too close to the central star, so that it is not too hot, and not too far away, so that all life would not freeze. In addition, according to our current knowledge, a few more conditions would have to be met for the emergence of life as we know it to be possible. For example, the planet should have liquid water on its surface and a sufficiently strong magnetic field to protect it from dangerous cosmic radiation. Researchers estimate that there could be around 40 billion habitable planets in the Milky Way. According to current knowledge, there are around 5 trillion in the entire observable universe. How likely are intelligent civilizations in space? In the 1960s, the U.S. astronomer Frank Drake came up with a formula that could be used to calculate how many technically advanced civilizations there should be in our Milky Way alone. However, the Drake formula named after him has a big catch. Most of the probabilities that go into this formula are unknown or only very rough estimates. One of the values, for example, is the probability of intelligent life emerging on an Earth-like planet. However, we do not yet understand how intelligent life could arise on Earth and what the probability is. Therefore, the Drake formula cannot be seriously used to calculate an exact probability of intelligent life in our Milky Way or in outer space. It is to be regarded rather as a thought experiment. The formula makes clear, even a tiny probability for the emergence of intelligent life on a certain planet is no obstacle for intelligent life in space. This is because this small probability is made up for by the fact that there are so innumerable Earth-like planets. This raises the overall probability again to the point where the existence of extraterrestrial intelligent life seems plausible. Why haven't we received any signals from aliens yet? If it is considered possible that there are other technically advanced civilizations in space, how can we find out? To answer the question, researchers have been systematically trying to receive extraterrestrial signs of life since the 1960s with so-called SETI projects. SETI is the abbreviation for Search for Extraterrestrial Intelligence, which could be translated colloquially as alien search. To do this, researchers use radio telescopes, some of which have receiving dishes several hundred meters in size. They are thus so sensitive that they could pick up even extremely weak radio signals. Meanwhile, Russian-born Silicon Valley billionaire Yuri Milner has also joined the search for extraterrestrial intelligence. With his Breakthrough Listen project, he is financing scientists who are searching for laser signals in addition to radio signals. This would enable technically advanced civilizations to communicate over long distances in space. Despite all efforts, however, no extraterrestrial message has yet been picked up, with one potential exception. On August 15, 1977, astronomer Jerry Emin evaluates the reception data of the radio telescope at Ohio State University and can hardly believe his eyes. In the printouts, a signal stands out from the usual noise. It is exceptionally strong and covers only a narrow frequency range, just as a radio station transmits only on a certain frequency. Jerry Emin is so amazed that he writes, "Wow!" next to the signal on the printout, hence the name. Did it come from aliens now? Theoretically it could be, but unfortunately the technology of that time was not sensitive enough. Therefore, the signal was too noisy to decide that. It could also come from a previously unknown astronomical event or from Earth. But even these alternative explanations are not completely convincing. Up to now, no other signal of this kind was received. At the end of the last century, the idea of the Great Filter came up. It says that each quantity of steps must be overcome, so that a civilization arises and lives then also long enough, in order to make itself noticeable in the universe. First of all, there must be a suitable planet, then primitive life must develop on it, which then evolves from the single-celled stage to multicellular organisms. From these then animal-like beings would have to develop, which learn to use tools and which develop their technology mastery in such a way that they create a highly developed civilization. This would have to exist long enough for them to invent the technology that would allow them to communicate beyond their planet. Eventually, this civilization might even leave its home planet to spread out into space. Each of these steps could be the Great Filter, a kind of barrier that prevents galaxy-colonizing civilizations from emerging. After all, if just one of these steps is extremely unlikely, it could explain why we haven't yet encountered extraterrestrial life. Perhaps even the emergence of primitive life forms is extremely unlikely, or the emergence of tool use, or some other step toward a space-colonizing civilization. The last possible filter would be that technically advanced civilizations have only a limited lifespan because something causes them to inevitably self-destruct after a relatively short time. In our case, it is not clear whether we have already made it with the emergence of intelligent life and have come through the Great Filter, or whether the Great Hurdle still lies ahead of us. Then our great challenge is not to destroy our basis of life ourselves, if we do not want to perish again soon. The coming generation of space telescopes could provide an answer to whether the Great Filter is already behind us or still ahead of us. Because if we pick up with them many signs from other technically highly developed civilizations, this would be a positive sign. That would mean that we have already overcome the hardest step with the emergence of intelligent life. Thus, we would have the potential to continue to exist for a very long time. However, if we find primitive life on other planets without also encountering technically developed civilizations, the conclusion would be depressing. That would mean that the emergence of life in space is relatively common, but that civilizations that develop from it quickly destroy themselves again. Because otherwise, one would have to find many of them. What could extraterrestrial life look like? Even on Earth, it is difficult to define what exactly life should be. The criteria that living organisms meet include growth, reproduction, metabolism, and energy absorption from the environment. And living things have a boundary to the outside world, such as a cell membrane. Crystals growing from mineral salt solutions already fulfill some of these criteria, such as growth and a clear boundary to the outside world, but they still lack reproduction. Viruses, for example, can do this, but they need host cells in which to reproduce. Are viruses therefore not life? With them, the demarcation between animate and inanimate is already more unclear. This example shows how difficult it is to define life precisely. On other planets, for example, it would be conceivable that life runs with completely different chemical processes than on Earth. One could in principle imagine a life chemistry, with silicon as one of the central elements instead of carbon. However, since we have never demonstrated such biochemically fundamentally different forms of life, they remain speculation for the time being. In the search for life in space, researchers are therefore concentrating on biosignatures, like those we know from terrestrial life. Biosignature is only the more scientific term for trace of life. These can be simple molecules, such as methane, which is often produced by bacteria, or more complicated organic molecules, such as those that make up our genetic material. But they can also be traces of fossilized bacteria or higher organisms, such as those found in very many rock layers on Earth. Is there life in our solar system? When we search for life outside the Earth, we first search for one of the most important bases of life as we know it, water. Mercury is therefore already ruled out. It is too small and has therefore too little gravity. All water, which perhaps once existed on it, evaporated therefore into the universe. Venus orbits a little further away from the Sun. It is larger than Mercury and therefore there is some water on it, but unfortunately in the form of sulfuric acid clouds. In addition, the temperature on the surface of Venus is around 450 degrees and the atmospheric pressure is almost 100 times higher than on Earth. All in all, very extreme conditions that make life very unlikely. Very close to us is the Moon. But on its surface, every drop of water would evaporate immediately. It is therefore dry as dust and water could exist there, if at all, only as ice in shady craters or under the surface. One planet that has long captured the imagination of astrobiologists is our neighboring planet, Mars. Astrobiologists are the researchers who search for life in space. Just over 100 years ago, it was even believed that a presumed Martian civilization had created a huge irrigation system. These are the famous Martian canals, but they eventually turned out to be optical illusions. The first Mars probes found only a dust-dry desert planet. In the meantime, however, we know that thick layers of water ice accumulate at the Martian poles, and further ice and perhaps liquid water are suspected in the soil. More than 3.5 billion years ago, Mars may even have had large rivers flowing through it, as evidenced by impressive valleys and canyons on Mars. It could have resembled the early Earth in terms of environmental conditions, and the life forms that may have evolved then could possibly still be dormant in the soil today. So far, however, no Mars probe has found clear evidence of life on Mars, whether past or still existing today. But a possible Mars biosignature has caused a lot of excitement. In 2004, the Mars rover Curiosity detected traces of methane in the Martian atmosphere. It could have been released by geological processes such as volcanic activity, but it could also be the long-awaited hot lead to life on Mars. This is because methane is released in large quantities by bacteria on Earth. Unfortunately, the methane measurements have not yet been confirmed beyond doubt. The European Trace Gas Orbiter, which has been orbiting Mars with its extremely sensitive methane measuring instruments since 2017, has not been able to detect any traces of methane in the atmosphere. Two possible explanations for the Mars rover's methane measurements are therefore currently being discussed. Methane could be formed on Mars near the ground, but very quickly degraded again before it can reach higher atmospheric layers. This is because the Trace Gas Orbiter can only detect it there. Or it could be a measurement error. Upcoming Mars missions will try, among other things, to solve the Mars methane mystery. Beyond Mars, life in our solar system will be limited. It is inconceivable on the large gas planets Jupiter and Saturn. And on Uranus and Neptune, it is extremely cold. The temperatures in the atmosphere drop below -200 degrees Celsius. On Neptune, the pressure in the atmosphere is so high that diamonds could form there from carbon-containing parts of the atmospheric gases, similar to how snowflakes form from water vapor here. We speak here of really extreme conditions, which make life seem impossible. However, astrobiologists are currently pinning their hopes on various moons in our solar system. For example, there seems to be a lot of water on Saturn's moon Enceladus and Jupiter's moon Europa. Both are covered by a layer of ice, but underneath they probably have huge oceans of liquid water. So we may yet discover life in our solar system. But if, then in all probability in a very primitive form. Or, at most, creatures like those from our deep sea, frogfish, for example, or self-luminous jellyfish that can cope even in complete darkness.